By a quick show of hands, how many of you in this room have ever used an antibiotic? How many of you have used it more than one time in your life? It's no surprise that many of you have been treated with a broad-spectrum antibiotic for many things, from strep throat to an infected wound. In fact, we've been successfully treating patients with antibiotics for over 70 years. Did you know, however, that according to the CDC, our overuse of antibiotics is creating drug-resistant bacterial strains that are becoming much more difficult to treat? As a biology major, I've become interested in the alarming rate at which our antibiotic treatments are losing their effectiveness. As the threat of antibacterial drug resistance increases, so must our desire to find new ways of approaching this potential crisis. Bacteriophage treatment is one such method that I'd like to shed some light on today. To some, bacteriophage may seem like some complicated term for some complex treatment, when in fact it's actually beautifully simplistic in nature. I'm going to explain to you exactly what a bacteriophage is, how it functions to treat a bacterial infection, and why this type of research is so very important to us today. To begin, we know that the bacteria that causes staph infection, let's say Staphylococcus aureus, is a bacterium that infects our cells, causing potentially fatal sepsis and illness. But what if we could actually engineer a virus that could infect the bacteria that's infecting us? Well, we can, and we have, and that virus is called a bacteriophage. They were first discovered in 1915 by Frederick Twort and Felix de Herel, and their use in treating against bacterial infections was evident then, but never really successfully done. Early research was conducted, but inconclusive, in the Republic of Georgia and in Russia. And in the 1940s, the United States began marketing antibiotics, and phage therapy research was abandoned. So to give you kind of an image that you can understand what a bacteriophage looks like, this is what it looks like. It has an icosahedral, that's the name of the shape, head on it. It's actually called a capsid. It has what we call a tail, which is this projection here. Then these projections here are called tail fibers, and they're what's used for attachment to the bacterial cell surface. And what it would look like is this virus that looks so big here is going to look really tiny here compared to this one bacterium, if that gives you an idea of how small this little virion really is. This is one bacteria, and this would be the virion, the little bacteriophage. Okay, they're kind of temperamental in the way that they function. For one thing, one single phage will only recognize and attach to one certain bacteria. So, for instance, say that it's a phage for Listeria, it's not going to attach to an E. coli. However, they can easily be modified in the lab to recognize the bacterium that you engineer it to treat. The bacteriophage, as I had explained before, attaches to the bacterium with its little tail fibers and injects its own DNA, its own viral DNA, into the bacterial cell. The viral DNA inserts itself into the bacterial DNA, and what that does is it forces the bacteria to stop doing its own processes and starts instead making more viruses inside of itself. Eventually, the bacterial cell bursts, releasing more viruses, more bacteriophages, so it successfully treats and kills this bacterial infection. Let's take a look at exactly why this therapy is so important for us today. Bacteria is becoming more resistant to drug therapy. This we know for a fact. We're effectively creating superbugs that will eventually run out of ways to treat. The CDC calls antibiotic resistance one of the world's most pressing health issues. In some instances, the antibiotics that we're taking, they do more harm than good. They don't differentiate between harmful and helpful bacteria. I mean, not all bacteria is pathogenic. Some of it is part of our natural body's flora. Some of it's designed to protect us or aid us in digestion. Killing that good bacteria can actually cause further illness and can result in longer hospital stays. The CDC claims the antibiotics can actually kill the sensitive, harmless bacteria and allow the drug-resistant bacteria to grow in severity and in number. Now, that's scary. Bacteriophage therapy, on the other hand, is very specific. It's kind of tailor-made to your illness. This may require more lab work to determine the type of bacterium we're trying to treat and to engineer the phage to actually treat it, but the financial cost is far less severe, I'm sure you'd agree, than the lives that will be lost to antibiotic-resistant bugs. Another problem with antibiotic treatment is that doctors are now in the habit of prescribing antibiotics for anything. You sneeze, antibiotic. You cough, antibiotic. Your knee hurts, antibiotic. Pediatricians, they have been known to prescribe antibiotics because they feel pressure from the parents of the sick children to prescribe something. Don't get me wrong, most of the time prescribing antibiotics is a good coverall for the physician, but as a population, we're looking at some really serious long-term effects that could be really devastating and, to be frank and a little dramatic, it could be devastating to mankind. And now that we understand a little bit about what a bacteriophage is and how it treats bacterial infections, let's discuss a little further the importance of the continued education and research in this field. Currently, the United States is not supporting any research in phage therapy, which is an absolute shame. In the Republic of Georgia, there's many facilities that are successfully engineering phages today that are treating and saving lives. And they're doing that while we are sitting on the sidelines and contributing further to the resistance issue. Right now, the CDC, the only effort we've really put forth is a public program that's called Get Smart, which it's a motion that helps doctors reduce the number of unnecessary prescriptions, unnecessary antibiotics that they prescribe and it's helped out by nearly 25%. So that you can get a grasp of the financial implications here, $1.1 billion just last year was spent on unnecessary prescription antibiotics for upper respiratory infections alone. That's $1.1 billion in 1 year on unnecessary drugs for one type of illness. That's not covering everything else we prescribe antibiotics for. I mean, the list is extensive. It's become apparent that we're only stalling the inevitable by decreasing the number of unnecessary prescriptions. What we truly need is the funding and educated specialists to begin a national program for the eradication of bacterial infections without the use of antibiotics. To summarize, antibacterial drug resistance is a serious issue. It's our responsibility, now that we have recognized the problem, to visit and revisit methods of testing bacterial infections without making superbugs. The most promising research comes from the field of bacteriophage therapy. I've explained what a bacteriophage is, how it can work for us, and what we need to do to move forward in this type of research. So I want to leave you today with a quote from a great scientist and one of my personal heroes, Carl Sagan, that I hope that the future scientists that work in this research will take to heart. Somewhere, something incredible is waiting to be known. Thank you all so very much for your time and for your attention.